Welcome guys to my channel. This is Chemistry with Min. Today,
Today's topic will be crystal structures. Before we discuss crystal structure, let's dive in first to the common phases of matter. Let's review about that. What is solid, what is liquid, and what is gas? Solid has definite shape and definite volume, and the structures of the particles are very close to each other. And there's and then liquid, it has a definite volume but doesn't have any definite shape. The particles are neither too close nor too far from each other. And meanwhile, while gas, it doesn't have a definite shape and volume. So the particles are very far apart. Crystallography is a branch of science that deals with the geometric description of crystals and their arrangement. It is crystals and the math used to describe them. What is crystals? Crystals are solid that consist of a periodic array of atoms, ions, or molecules. As you can see here in the picture, both graphite and diamond have just consist of um, carbon. However, the difference is the structure arranged. What is a perfect crystal? A perfect crystal is an idealization that does not exist in nature. In some ways, even a crystal's surface is an imperfection because of the periodicity is uninterrupted there. We know that each atom undergoes thermal vibration around their equilibrium positions for temperature. T is greater than 0 Kelvin. This can be also viewed as imperfections. Why study crystal structures? The properties of the material are directly related to their crystal structure. The significant property with difference between crystalline and non-crystalline materials having the same composition versus diamond and graphite. Space lattice plus basis is equal to crystal structure. But what is crystal structure? Crystal structure is formed by putting the identical atoms on the point of the crystal lattice. So what is a crystal lattice or space lattice? It is a regular periodic arrangement of points in space, and it is a purely a mathematical abstraction. This group of atoms is called bases. There are 14 Bravais lattices and 7 crystal types. So the crystal types are cubic crystal system, where you will find the FCC, BCC, and CS, hexagonal crystal system, triclinical crystal system, monoclinic crystal system, orthorhombic crystal system, tetragonal crystal system, and lastly, trigonal crystal system. As you can see there in the picture, the different structure, but we'll just focus on the cubic crystal system. What is crystalline solid? Crystalline solid is a solid form of a substance in which the atom or molecules are arranged in a definite repeating pattern in 3 dimensions. So a single crystal have an ideally have a high degree of order or regular geometric periodicity throughout the entire volume of a material. Types of solid crystals. So we have amorphous, polycrystalline, and single crystal. With amorphous, it is described as with few order within a few atomic and molecular dimension. For example, glass, plastic, resin, and sugar. While polycrystal, with multiple single crystal regions or grains separated by grain boundaries, as you can see here in image B. So some examples of that are rock, sand, metal, and salt. While single crystals is described with geometric periodicity periodicity throughout the entire material. So, example, rock salt, quartz solid, calice. Under crystalline solids, we have ionic crystals, covalent crystals, molecular crystals, metallic crystals, and atomic solid crystals. So those are some of the classification under crystalline solids. So let's find out the difference between those different classifications. So ionic solids is made up of positive and negative ions and held together by electrostatic attraction. It is characterized by a very high melting point and brittleness and are poor conductors in the solid state. Some examples are sodium chloride, zinc sulfide, calcium chloride. So those are a few examples of ionic solids. Covalent solids are made up of atoms connected by covalent bonds. The intermolecular pores are covalent bonds as well, characterized as very hard and with very high melting points, and being a poor conductor. Some examples of a covalent solids are diamond, quartz, and graphite. Metallic solids are held together by a high density of shared delocalized electrons, resulting in metallic bonding. It is characterized by high melting points, can range from soft and malleable to hard, and very good conduct and it is a very good conductor of electricity. Molecular solids are made up of atoms or molecules held together by London pores, dipole to dipole pores, or hydrogen bonds, characterized by low melting points and flexibility. For example, sugar, ice water, and dry ice. Atomic packaging factor, or APF, it is defined as the ratio between the volume of a basic atom of the unit cell to the volume of the unit cell itself. So all you need to do is divide the volume of atom and the unit cell. In the cubic system, we have simple cubic, body-centered cubic, and face-centered cubic. So let's define each of them and what's the difference between CS, BCC, and FCC. Simple cubic structure. What is it? So it has an AAAAA structure. Simple cubic has one lattice point, so it is a primitive cell. The coordination number of a simple cubic is 6, and it has an atomic packaging factor of 52%. Remember this, guys. This structure is the least efficient. There is only one element that is a simple cubic structure, which is polonium. But body-centered cubic structure, or we define it for you to easy to remember the body-centered cubic structure is that it has one whole atom in the middle. Okay, so BCC has two lattice points. It is a non-primitive cell, and at the same time, the coordination number is 8, and neighbor, um, some of example of body-centered cubic structure is lithium, sodium, and it has 68 atomic packaging factor. Face-centered cubic. So, so the atoms are arranged at the corners and the center of the base of the cell. So it has an ABC, ABC, ABC structure. And then the example of this is copper, aluminum, gold, silver, and it has four atoms. The packing factor, atomic packing factor is 74%, and has coordination number which is 12. Hexagonal close-packed has a form of AB with the coordination number of 12. It has six atoms in the unit cell. So how is it six? So you can see here one half in the top and then one fourth in each sides. So in the middle also one half. So you can see that here. So six corners and then six um, three atoms and then a half space. Okay. And then the atoms can attain a lower energy and a more stable condition by forming HCP structure. The relationship between the atomic radius and the edge length in three different cell units. So in SCC, the atomic radius is equal to this. You can see how it was formed. So all you need to remember is I won't do math too much on this subject, but just remember that SC or simple cubic has 2R, 2, 2R as a radius, and then for BCC 4R over square root of 3, and then for the FCC square root of 8R or radius. So just remember those values. You will be needing that later in our computation part. So before we go to the equations part and the problem solving, let's summarize the lesson here, the important part. So SC or simple cubic has a relationship A equals 2R, atoms per cell, only one, coordination number, which is 6, packaging factor, which is 0.52, example, which is polonium. While in BCC, remember this value, okay? A is equals to 4 over 3, square root of 3, reduced. It has two atoms, coordination number, which is 8, packaging factor, which is 0.68, while in FCC, a while ago I said square root of 8, but it's still the same in here, which is 4 over 2 square root of 2. If you do the math, it will show 8 also. So atoms per cell is which is 4, coordination number which is 12. While in HCP, so we won't do calculation for HCP. It's a bit complicated, but the important thing that you know that the atomic cell per number, which is only 2, and the coordination number, which is 12, and the packaging factor, which is 0.74 or 70%. So this, remember, the packaging order of SCS, which is AAA, BCC, it's ABABAB, um, FCC is ABC, 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 and lastly HCP, which is AB, 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 which is the packaging arrangement of those crystal structure. So let's move on to the calculation part. All right, let's solve this problem. Prove that the packing efficiency of simple cubic is 52%, BCC 68%, and FCC 74%. So do you still remember the formula for atomic packaging factor? Hey, let's do this. So now, okay, okay. So we want to see if it's true. So remember this. All right. Do you still remember this? The summary. It's really really important that you you memorize this, especially this one. Okay. Now that's out of the way. So let's start. Okay. A P atomic packaging factor. Let's start with CS first. All right. So 4 over 3 square root of 3. Uh, you know why? Why is this like this? This is the volume of sphere or the volume of atom. There you go. Now that we have this, now then A3. So now that we have this, remember a while ago we said that 2A is 2R. Am I correct? Let's check it again. Yep. All right. Now that we know that A is equal to 2R, and we can substitute this here. So it would be 4, 3, half 3 divided by 2R squared. So that would cancel out the radius. So that would be 8, 4 over 3, pi. And then you will get 52%. All right. Let's try. Let's try another one. The BCC. Let's try the BBC. Okay. So we want to show if this is 68, right? All right. So how many atoms again that we have A and BCC? Let's check. It's 2. So 2. What's the volume of a sphere or the atom? 4, 3, R 3. There you go. Then let's divide it by A3. Now, what's again the edge length? This is edge length, okay, guys. Forgot to tell you about that. So the edge length would be 4 over 3. All right. Okay. A is equal to 4 over 3. There you go. So let's substitute this here. So 4 over 3 there. Oh yeah, I forgot the R. R, there you go. R, and then 2 times 4 over 3 pi equals to 3R. It will cancel the R's. So it will leave us to 2 times 4 over 3 pi divided by 4 over 3, wait, squared. So that would lead us to 68%. All right. So do you get it? Do you get it, guys? All right. Let's move on to FCC4. Same procedure, but remember the atom for FCC is 74. Correct? Yeah. So let's start again. So let's do this. So what is the atomic packaging factor? So we have four atoms times the volume of the atom divided by its length. So we know that this is pi r3 pi r equals a. So now that we have this, the equation will look like this. And then 3r will be cancelled. So the final answer would be 74%. Sorry, 74%. There you go. Okay, let's solve another problem. Okay, gold forms a FCC crystal structure and has the atomic radius of 8.73 to the negative 12. So calculate the density of gold. So we only have the radius, all right? So we want to find the density. Remember, density is equal to mass over volume. So we can get the mass by what we have known is this. We have four atoms, and then we'll divide it by 0.2 or the Avogadro's number per atom. After atom, then we'll have to multiply it by the atomic mass of gold. So what's the atomic mass of gold? So 196. So now that we have this, let's divide it by the volume. So what is the volume? So we know A3 is equivalent to, so we know that A is equivalent to pi r. There you go. So all we need to do is this 8r. So we input the value of the radius 8.7 to the negative 12, and then we'll get our density. So to have a clearer view, I have created a better slide. See here? This is the mass of the gold, the Avogadro's number. We have to convert first to get the volume. This. So you won't get confused. Um, Square root of 8 is also equivalent to this. So now that's the final answer. The density is 9.39 grams per centimeter. Let's try one last more, okay? All right, let's try another problem. Sodium has a density of 0.971 grams over square meter and crystallized with a body-centered cubic unit cell. So, what is the radius of a sodium atom and what is the edge length of the cell? So, we need to solve this, okay? All right. So, we're given just the density and then the rest, and we know that it's BCC. So, let us set up the equation. So, let's set up the equation here. So, all right. So we know that the density is equal to volume. Now, so the mass is two atoms times the Avogadro's number times the atomic mass of sodium. The atomic mass of sodium is 22 grams. Oh, so that's what we're gonna get. So divided by the volume, divided by the density. So remember, we're missing this. So the equation will be this. There you go. Now, okay. With that, we can solve now the edge length. So let's do this. So 2 divided by Avogadro's number. To the Avogadro's number times 22. So just give me a minute. I'm still calculating it. Times 2, 22. So we got so the density will be 7.3. Sorry, density would be 7.7.3. Sorry, volume is 7.3 to the negative 23. That would be our volume. That's our edge length. That's our volume. Now that we know the volume, we need to find the radius. So remember, the volume is A3. So that would be 4 over 3 R.